In the first place, you write your code in a way that is easy to read, understand and maintain. But sometimes you arrive at a point where your application takes too much time for some action. You now probably want to optimize it. But, and this is important, never try to guess where the performance bottleneck is. Even if you can reduce the time complexity by using a more clever algorithm, measure the execution time before and also after your optimization. Let's have a look at an example. First, we create a timer class that we can use as a stopwatch to measure execution time of different parts of our code. Now we search for a specific element in our vector using linear time complexity. Then we do the same but in logarithmic time by using a set that usually is implemented using red-black trees. Always verify that the optimization really helps. This is even more important if your change increases code complexity. When it did not help, revert it. And for more complex algorithms than the one we just wrote, you should always use a profiler to find the critical code section and use real data for your application to do so. Otherwise, you will end up wasting time and disfiguring your code in places where it is not needed. For Windows, I can recommend Very Sleepy. It's a very lean piece of software, but it does its job quite well in most cases. Under Linux, I use sysprof. Even experienced programmers are notoriously bad at guessing where the real performance bottlenecks are. This partly comes from the fact that compilers do a really good job at optimizing code. Not only function calls can be inlined, but there also happen some crazy optimizations across multiple compilation units. So do not try to outsmart your compiler. Even if you succeed at some point, it is possible that with the next update your compiler will defeat you again. Especially if you changed the CPU architecture and suddenly new SSE instructions are available. An additional thing that makes performance difficult to predict is cache locality. Accessing values in the memory can have very different costs, depending on how near it is to the part of the memory you accessed last. A linear run-through memory is orders of magnitude faster than orderless access. This also is the reason why the vector version of your small test program is so much faster than the set version. stdvector guarantees all elements to be consecutively in memory. Most stdset implementations allocate nodes to their internally used red-black tree in separate memory locations. A good example for this effect is traversing an image in memory whose pixels usually are stored in successive lines. So going through the pixels row by row like this is much faster than going column by column like that. Even though the actual calculations performed are the same. So when using a profiler to find bottlenecks, your code should of course be compiled with speed optimizations enabled. For Clang and GCC it is the O3 command line flag I just used. Okay, but this all holds true for every type of code. Are there any special things one has to consider when optimizing functional code? Yes, at least some. When writing pure code, especially when transforming over or filtering sequences or other containers, you end up with copies, since pure functions never operate in place. They do not mutate the input. To improve cache locality, prefer stdvector over stdlist as containers you mostly want to transform on. And think of the additional memory used by the copies. If you find out you really have to use an imperative implementation, perhaps mutating in place, you should go for it. C++ is a multi-paradigm language, so we can harvest the advantages of both worlds. Just make sure the impureness does not leak to the outside of the function that it resides in. It is possible to create functional data structures that can be changed without having to be copied completely. For example, inserting an element into a dictionary would return a new dictionary that shares most of its state with the original one without having it changed. Up to now, the standard does not provide these kind of structures, but some libraries do. All in all, the most important thing when optimizing functional code is the same as when optimizing imperative code. Always use a profiler.